In your previous lesson, you learned how to calculate chemical reaction rates. In this lesson, you will be considering the following questions. What causes a reaction to occur? And why do some reactions go quickly and some slowly? By the end of this lesson, you will be able to explain the collision theory of chemistry. As in the picture, if you get a collision, you get a reaction, providing there's enough energy. By the end of this lesson, you will also know the various factors that affect the rate of reaction. So I ask again, what causes a reaction to occur, and why do some reactions go quickly and some slowly? It all has to do with collision theory, which states that a chemical reaction occurs only when the reacting particles collide with one another. Kinetic energy, the energy of motion of the molecules, is needed to break chemical bonds first, and this energy must be high enough to get the reaction going. If you take a 1 ml sample of gas at room temperature, about 10 to the 28 collisions per second would happen. If each of these collisions resulted in a reaction, then all the reactions would be complete in about a nanosecond. But only a fraction of collisions between particles result in a chemical reaction, because these two criteria must be met. For a collision between reactant particles to be effective, first, the orientation of the reactants, called collision geometry, must be favorable, and second, the collision must occur with sufficient energy. If these two criteria are met, we say that the collision between reactant particles has been effective. However, if even one of the two criteria are not met, the collision is considered ineffective. Let's first look at effective collisions. We need to keep the following points in mind when we consider effective collisions. A chemical system consists of particles, which are atoms, ions, molecules, etc. They are always in random motion at various speeds. The average kinetic energy is proportional to the temperature of the sample. As the temperature increases, the kinetic energy of the particles increases. Chemical reactions involve collisions of particles with each other and/or the walls of the container. Effective collisions require bonds to break and new ones to form, and it is essential that they have the following. Effective collisions must have the correct orientation of reactants and sufficient energy. But what if it doesn't have at least one of these things? It is an ineffective collision, a collision in which the particles rebound from each other and there is essentially no change to them. The rate of reaction, then, depends on the frequency of collisions and the number or fraction of collisions that are effective. Let's now look at these two criteria of effective collisions, the correct orientation or reactants, and sufficient energy, in greater detail. Effective collision criteria number 1 is the correct orientation of reactants. That is, for a chemical reaction to occur, reactant molecules must collide with the correct orientation relative to each other, called collision geometry. In this diagram, we are shown the reaction of nitrogen monoxide, NO, with ozone, O3, which produces nitrogen dioxide, NO2, and oxygen, O2, when the reactants effectively collide. Nitrogen atoms are depicted in blue, oxygen atoms in red. In the first collision shown on the top going across, nitrogen monoxide and oxygen are on a collision course with each other. However, the orientation of the molecules is such that they essentially bounce off each other and do not react. The collision is ineffective. The same happens in the second middle collision. The collision is ineffective because the molecules are not ideally aligned and therefore cannot react with each other. Only the bottom collision results in a reaction because the molecules have collided with the correct orientation relative to each other. In this effective collision, the angle at which the nitrogen atom in the nitrogen monoxide molecule approaches the oxygen atoms in ozone is the same angle that is formed in the nitrogen dioxide molecule. Effective collision criteria 2 is sufficient activation energy. For a chemical reaction to take place, reactant molecules must also collide with sufficient energy. Let me put it another way. Without enough oomph, no reaction is going to occur, even if the molecules are correctly oriented. Scientists have come up with the term activation energy to describe this. Activation energy, or E sub A, is the minimum amount of collision energy required to initiate a chemical reaction. Collision energy depends on the kinetic energy of the colliding molecules, that is, the energy they have in motion. This diagram here is called a Maxwell-Boltzmann distribution. It plots the number of molecules against their energy. A similar graph is found in your textbook in figure 6.9 on page 366, although that one plots fraction of collisions against energy. The dotted line indicates the activation energy. It is at that energy that collisions become effective and a reaction occurs. The shaded part of the graph indicates the fraction of the total collisions that have energy equal to or greater than the activation energy. The two distributions represent two different reactions, both with the same number of molecules, but at different temperatures. The areas under the two curves are the same, but the temperature in reaction T2 is higher than the temperature of the reaction in T1. Therefore, the average energy of the molecules under curve T2 is greater. There will be more particles with higher levels of energy and with enough energy to start a reaction. We can tell this from the graph because the area under T2 to the right of EA is larger than the area under the graph for T1. You will not be drawing any Maxwell-Boltzmann distribution curves, but you will be learning how to draw potential energy curves. These are used to represent the progress of chemical reactions. When interpreting or drawing these graphs, keep the following in mind. Moving from left to right, the left flat line shows that molecules are moving toward each other. As they get closer, there are repulsive forces and they slow down just a bit, and some kinetic energy is changed into potential energy. The potential energy increases as reactants become closer. If they are still moving fast enough, their bond structure rearranges. They form an activated complex, called transition state on your diagrams, which is an unstable molecule with its own geometry. It is unstable because it contains maximum potential energy possible. So when the collision energy is greater than or equal to maximum potential energy, reactants will transform into a transition state. At this high peak of potential energy, an activated complex or transition state may either revert to reactants, go back, or proceed to form products. Another way to say this is products then form if there is an effective collision, or reactants will reform if the collision is ineffective. Remember, for exothermic reactions, the reactants have greater energy than the products. And for endothermic reactions, the reactants have lower energy than the products. That should remind you of enthalpy. When we talk about activation and energy and enthalpy, we need to know that the activation energy of a reaction cannot be predicted from delta H or change in enthalpy. Delta H for the reaction is the enthalpy change for the total reaction. It is determined only by the difference in potential energy between reactants and products. A negative delta H means energy decreases. Positive delta H means energy increases. Negative delta H means the reaction is exothermic. Positive delta H means the reaction is endothermic. The energy needed to start a reaction is called the activation energy of the reaction, and it is determined by analyzing rates of reaction at different temperatures. Just imagine a ball rolling and approaching the hump on the graph with a certain quantity of kinetic energy. The kinetic energy is transferred into potential energy as it goes up the hump. If there was enough kinetic energy, the ball would go over the hump. If there is not enough kinetic energy, the ball will roll back again. It is important to note that reactions with low activation energy occur quickly. It is easier for them to do so because less energy is required to make a reaction occur. Reactions with high activation energy occur slowly because so much more energy is required to make a reaction occur. Potential energy diagrams can represent both forward and reverse reactions. Look at the diagram for potential energy here and follow the reaction progress from left to right. This is for a forward reaction. Look at the diagram again, this time from right to left. This is for the reverse reaction. In the forward reaction, carbon monoxide reacts with nitrogen dioxide to form carbon dioxide and nitrogen monoxide. Change in enthalpy is minus 226.1 kilojoules, an exothermic reaction. The forward activation energy of this reaction, denoted by E subscript A forward in the diagram, is the difference in energy between the reactants and that of the activated complex at the top of the peak. In the reverse reaction, looking at the diagram from right to left, carbon dioxide and nitrogen monoxide react to form carbon monoxide and nitrogen dioxide. Change in enthalpy is positive 226.1 kilojoules, an endothermic reaction. The reverse activation energy of this reaction, denoted by E subscript A reverse in the diagram, is a difference in energy between the reactants, which are now carbon dioxide and nitrogen monoxide, and that of the activated complex at the top of the peak. Delta H of the reaction is related to both the forward activation energy and the reverse activation energy in the following way. The forward activation energy minus the reverse activation energy equals a change in enthalpy for the reaction. Looking at the equation, you can see that if the forward activation energy is smaller than the reverse activation energy, delta H will be negative, and the reaction is exothermic. If the forward activation energy is greater than the reverse activation energy, delta H will be positive, and the reaction is endothermic. Given what you have just learned, would you be able to draw a potential energy diagram for an exothermic reaction? Pause the video for a moment and draw a diagram, including the labels for the X and Y axes, reactants, transition state, products, activation energy, and enthalpy of reaction. Does your diagram look similar to this? And which would be greater for this reaction? The forward activation energy or the reverse activation energy? The reverse activation energy is greater than the forward activation energy. Next, we will look at factors affecting reaction rates. Any factor that increases collision frequency increases the chemical rate of reaction. There are 6 factors we will consider: the nature of reactants, concentration, temperature, pressure, surface area, and presence of a catalyst. When we talk about the nature of reactants, we are talking about the types of reactants involved and the types of bonds that are breaking and forming during a chemical reaction. Reactions between ions and solutions tend to be faster than those of molecules because, firstly, in solution, ions dissolve and move freely, and secondly, the positive and negative charges attract each other. Concentration also affects reaction rate. Higher concentrations of reactants will generate a greater number of effective collisions. As the reaction proceeds, the concentration of reactants decreases and the concentration of products increases. When temperature increases, there are more particles with sufficient energy needed for a reaction. Higher temperature gives the reactants higher kinetic energy. The reactants are moving faster. This was discussed earlier when we looked at the Maxwell-Boltzmann distribution. When there are gaseous reactants, the number of collisions in a certain time interval increases with increased pressure. Recall Boyle's law, which says that pressure increases as more molecules are added when the volume is constant, and that as volume decreases, pressure increases. Surface area of the material also affects reaction rate. The more surface area, the more locations for a collision to occur. Think of how quickly sugar dissolves, depending on how much surface area it has. Granular sugar dissolves faster than a lump of sugar. And finally, the presence of a catalyst greatly increases reaction rate. A catalyst is a substance that increases a reaction rate without being consumed by the reaction. Adding a catalyst will significantly reduce the amount of energy needed because it significantly lowers the activation energy. Lowering the activation energy of a reaction increases the proportion of particles that will have enough energy to react, as shown in this diagram. A catalyzed reaction has the same reactants, products, and enthalpy change as the uncatalyzed reaction. However, it requires much less energy than an uncatalyzed reaction. This has many advantages, especially industrially, as it means reactions are more efficient and the catalysts are economical also. Now that we are at the end of this presentation, can you answer the following questions? What is collision theory? What makes a collision effective? What is activation energy? How is the progress of a chemical reaction represented? How is enthalpy of reaction related to both forward activation energy and reverse activation energy? What are the factors that affect reaction rates, and how do they do so? For homework, read Catalysts in Industry, pages 375 to 377 of your text. Do practice problems on page 371, numbers 13, 14, 18, and 20. Read section 6.2 review on page 379, and on the same page, do questions 2, 4, 6, 10, and 12.